Okay, so here is an example of where we're looking for equilibrium. When you're looking for equilibrium, you want all of the forces, when you add together the horizontal forces, you want those to add to 0, and adding together the vertical forces, you want those to add to 0. Okay, so we have 3 people playing tug of war. The first one is Joey, so let's do his vector. So Joey's vector in component form is, do a quick sketch, 60 newtons at 210 degrees. Okay, so that is 60 times cosine of 210 sine of 210. Okay. And then if we do Simon's, is 30 newtons at 45 degrees. Simon is 30 times cosine of 45 sine of 45. Okay. And then we are looking for Austin's. We don't know his force. Okay, so it's the magnitude of however strong he's pulling it. And we don't know his direction. Okay, but we can figure that out. So I know that I want them to be at equilibrium, so that means that my Joey vector plus my Simon vector plus my Austin vector, I need all of those to add to 0 horizontal force and 0 vertical force. So what I have so far is, I'm not going to keep switching colors. I have 60 cosine 210. Let's do horizontal. 60 cosine of 210 plus 30 cosine of 45 plus f cosine of theta. So this is the horizontal component of Austin's vector. I need those to add to 0. Okay, so these are unit circle values, but kind of for simplicity and generalization, I'm just going to plug those in the calculator. So this gives me, these added together are negative 30.748 plus Austin's horizontal force. And that gives us that the horizontal component for Austin is 30.748 newtons. Okay, and we're going to do the same thing for vertical. 60 sine of 210 plus 30 cosine of 40, or sorry, I did that last time too. 30 sine of 45 plus f times sine of theta. So this is the vertical component for Austin, needs to be 0. So when I add these together, I get negative 8.787 plus Austin's vertical component equals 0. So the vertical component for Austin's tug of war vector, I keep writing cosine, is 8.787 newtons. Okay, so now I can actually write Austin's vector to be 30.748, comma, 8.787. Okay, so what that means is we have this vector going on, right, where this is that 30.7 and this is the 8.8, just rounding. We're going to use the exact ones in our calculations, but what we need to figure out is the magnitude of this, which again we just do Pythagorean theorem because the length of the vector signifies the strength of the force, and then we need to figure out the direction. So we need to figure out theta, which is the rotation from the positive x-axis, because we're going to use rotation from the positive x-axis because that's how it was given to us in the original problem. So that kind of indicates to us if we're going to do theta or if we're going to do a bearing. So if I want to find the magnitude, so how strong is Austin? we're going to do Pythagorean theorem. And that's going to give us 31.98 newtons. So that's the magnitude, so that's how hard he's pulling. And then we want to figure out the direction he needs to pull so that the forces end up in equilibrium. So to do that, we do theta is equal to tangent inverse of 8.787 over 30.748, which when you plug that in the calculator gives you 15.95 degrees, which is the reference angle, but since we are in the first quadrant, that's just our solution. So we have our force is 31.98, and the direction of the force is 15.95 degrees from the positive x-axis.